We've been looking at graphs, we've been analyzing graphs, and now we're continuing to look at graphs and determine different aspects about them. And a couple of the things that we're looking at in this lesson is whether a graph is continuous, meaning it's a smooth curve, or basically that you don't have to pick up your pencil in order to draw the whole thing. And we're also going to be talking about end behavior, meaning how does this graph behave as it goes all the way to the left, and how does this graph behave as it goes all the way to the right. So first we're going to talk about whether a graph is continuous and how we can test whether it's continuous. And if it's not continuous, we can test what kind of discontinuity it is. So there's infinite discontinuities where it's either approaching positive infinity or negative infinity as it approaches the point of discontinuity, or there's a jump discontinuity where there is a value for the f of c, if you will, of where that point of continuity breaks. So there is a function value, but as I approach that value from the left and as I approach that value from the right, the values are two different things. And then finally, those two discontinuities are considered non-removable because just making the graph defined, like a lot of times a graph will be discontinuous because there's something that's undefined at that point. Fixing that point doesn't fix the discontinuity in a non-removable discontinuity. And so then at the final cluster of bullets on your screen, you basically see the test for how to check whether a function is continuous. If I plug in a value for x, I actually get an answer. That's valuable. And as I mentioned earlier, my f of x has to be approaching the same value from both directions. And if all of the stuff that I've just said sounds like a bunch of gobbledygook, I get that. And of course, it's my hope that as I go through the next few examples, that gobbledygook becomes a little bit more clear and the language that we're using becomes more manageable. In this example, we are identifying whether a graph is continuous at x equals 0. So my graph is f of x equals x to the third. Now I don't have a graph, but it is asking me to use the continuity test. So the first part of the continuity test is to check whether f of 0 exists. So can I find the f of 0? If I plug in 0 for x, can I take 0 and raise it to the third power mathematically? Yes, I will get 0. So that's good. The second and third part of the test for continuity are to check what f of 0 approaches coming from the left and coming from the right. So here's what I mean by that. If I'm considering 0 on the number line and I am approaching it from the left, then a couple of numbers that I could test for x might be -1 and -0.5. Okay, so I'm going to plug in -1 for x. I'm going to plug in -0.5 for x. And part of what I'm testing for is, am I getting closer to 0 as I plug in those points? Okay, so f of -1 is -1 to the third power, which is -1. Well, that's kind of close to 0, so that looks promising. And then I check f of -0.5. And if this is going to look promising for f of 0 to be a point of continuity, then my answer is going to be even closer to 0. Okay, so I take this negative 0.5 and I raise it to the third power, and I get negative 0.125. Oops, too many negatives. So as I'm approaching 0 from the left, I am in fact getting closer to f of 0 being 0. So that looks good so far. Now I'm going to approach it from the right. And as I approach it from the right, some numbers that are really close to 0 might be 1 and positive 0.5. When I evaluate f of 1, I get 1 to the third power, which is 1. When I evaluate f to the 0.5, I get 0.125. And once again, as my x's are getting closer to 0, my function values are also getting closer to 0. So that's another part of the continuity test. And since these are approaching 0, and these are approaching 0, and this is 0, that means that the function is continuous at f of 0. My bottom line answer is that it's continuous at 0. And this whole process that I went through was the justifying using the continuity test. Take a moment and work through the your turn below. Once again, we're determining if a function is continuous at a given x value. We're justifying using the continuity test. This time, if it is discontinuous, they are asking us to identify what kind of discontinuity we have. Now this time I've added a table, and I think this might help make things make sense if the last example of testing for continuity was a little bit strange. Okay, so once again, the continuity test requires that I find a function value. So if my x value is 0, then I'd be finding the function of 0, and I'd be plugging in 0 for x. So that would be 1 over 0 squared, and that is undefined. So since there is no function value at the x value of 0, right away I know that it is not continuous. However, since the problem is asking us for what kind of discontinuity, we're going to continue. We've already talked about what kind of x values approach 0 from the left and what kind of x values approach 0 from the right. So I'm just going to use those values again because they're good values. -1, and -0.5. So I'm going to take -1 and plug it in. And I would have 1 over -1 squared being 1. And I'm going to plug in that -0.5 and square it, and I'll have the function of -0.5 being 1 over -0.5 squared which is 4. So as I'm getting closer to 0, like -1 and -0.5 are getting closer to 0, my y values, my function values, are increasing. And so it looks like that might be increasing by quite a bit. Let's look at this function coming from the right. So coming from the right, I'd be looking at 1 and 0.5, and using your number sense, I would hope that you'd notice that I end up with the same two values, 1 and 4. So because as I approach 0, I am getting bigger and bigger, this is an infinite discontinuity. This time I'm testing for whether the function is continuous at 2. So my x value this time is 2. And in this piecewise function, I'm going to take that 2 and plug it into the second piece of the function. So f of 2 would equal to -2, which is 0. So f of c does exist. F of 2 exists. Now I need to approach 2 from the left, and I need to approach 2 from the right, and see if those values that they're approaching are also 2. So approaching this from the left, I have 1 and 1.5, and when I find the function of 1, I'm plugging it into still the second part of my function. So I have 2 minus 1 is 1. And then in the second one, I have 1.5. And I'm finding 2 minus 1.5. Whoops. And that gives me 0.5. So as I'm approaching 2, my x value that I'm testing, as I'm approaching it from the left, I am getting closer to my function value at 2. I am getting closer to 0. So that looks promising. Now I have to approach it from the right. So approaching 2 from the right would be 3 and 2.5. So let's find the function of 3. When I find the function of 3, I have to plug it into the first part of my piecewise function. And when I plug it into my piecewise function, I have 5 times 3 plus 4. And that is 19. When I find my function value at 2.5, I have a function of 2.5 is 5 times 2.5 plus 4. And that's 16.5. And that's still not very close to 0. But just in case you are maybe the kind of student that would question, which is fine, and say, you know what, it's not really close to 0, but it is getting smaller. I'm not quite sure if it's not approaching 0. So let's try one more point. You see that I've written down 2.1. That's a little bit closer to 2, approaching from the right. So we'll see what happens here. The function of 2.1 would be 5 times 2.1 plus 4, being 10.5 plus 4 is 14.5. And that's still not very close to 0. I don't think that this is really approaching 0. It might be approaching 14. So even though I have a function value at 2, we've determined that it is not continuous. And notice that while it's approaching 0 when I'm coming to 2 from the left, when I'm approaching 2 from the right, it's coming from a completely different direction. So this is a jump discontinuity.